All right, welcome back, everyone. For today's deep dive, we're looking into something that might seem, well, a little unusual at first glance.
Oh, what's that?
Well, we're going to be diving into the connection between logic and probability. And I know, I know as philosophers, logic, that's our bread and butter, right? It's all about those solid, unbreakable truths.
Absolute certainty, yeah. The bedrock of reasoning.
Right. But probability, that's all about chance and uncertainty, those shades of gray.
A world where things could be this way or that way.
Exactly. So to think these two could be related might seem a bit weird.
I can see how that initial reaction makes sense. When you're used to dealing with those necessary truths, those ironclad deductions, introducing something as slippery as probability can feel like, I don't know, mixing oil and water.
It does. But trust me, what we're going to unpack today, it's not about forcing them together. It's more like discovering these hidden passageways between them. We'll be drawing heavily from the Stanford Encyclopedia of Philosophy's entry on logic and probability.
It really is a comprehensive piece, covering a lot of ground.
It is. But don't worry, we'll guide you through it, focusing on the key points. And for you, our listeners, especially those of you with that strong philosophical background, you're going to see how formalizing this whole idea of uncertainty has a history that goes way back. It's a real challenge to those simple notions of how we think. It forces you to confront the fact that most of our reasoning, it's not in that black and white, perfectly certain realm.
Right, it's a move away from thinking about the world as it must be and stepping into the world as it might be, which, when you think about it, is a very philosophical move.
Absolutely. Okay, so let's start with that first impression, that logic and probability, they just don't mix. Logic, it's all about the form of arguments, right? If the premises are true and the argument's valid, the conclusion has to be true.
Deductive validity, the holy grail of reasoning.
Exactly. No room for doubt. Probability, on the other hand, it throws numbers into the mix. It assigns degrees of likelihood to events, and, well, the world just doesn't seem to work in absolutes.
It's that shift from qualitative to quantitative that can feel jarring.
Right. But here's where it gets interesting. Despite that seeming difference, there have been, and still are, some incredibly bright minds who see a deep, deep connection between them.
Thinkers like De Morgan, Boole, Ramsey, De Finetti, Carnap, even more contemporary figures like Jeffrey and Howson.
Yeah.
All of them saw something profound in the relationship between logic and probability.
Yeah. Some even suggested that probability could be thought of as like a type of logic itself.
A logic of uncertainty, if you will.
I like that, a logic of uncertainty. And this isn't some new fad. I mean, Boole, he tried to build probability right into his logical system.
He did. And that really points to a long-standing philosophical struggle. How do we make sense of a world where absolute certainty is often out of reach?
Right. We rarely have all the facts. Okay, now, the Stanford Encyclopedia entry makes a really important distinction right at the start. It separates probability logic from inductive logic. And this might seem like we're splitting hairs, but I think it's crucial for us to get this straight.
Oh, it's definitely crucial. Both deal with likelihood and uncertainty, sure. But their underlying logic, that's where the real difference lies. Deductive logic, which is where probability logic, as we're discussing it here, fits in, it's all about preservation.
Preservation of what, though?
Well, in classical logic, it's the preservation of truth. You start with true premises, valid argument, you end up with a true conclusion. No wiggle room.
Okay, that's the standard picture.
Now, probability logic, it keeps that idea of preservation, but shifts the focus. Instead of truth, it's about preserving probability.
So instead of asking if the conclusion is guaranteed true, we ask, how certain can we be about the conclusion based on the certainty of our premises?
Exactly. It's not about making a conclusion likely based on evidence, which is what inductive logic tries to do.
Right, like, the sun has always risen in the east, so it'll probably rise in the east tomorrow. That's inductive reasoning. But that conclusion, it's not guaranteed by the premise, even though it seems very, very likely.
That's the classic example of induction. And it's different from what we're talking about here. Probability logic, at least how the authors of the entry, Adams and Levine, see it, it's a branch of deductive logic.
Okay, so we're still in the deductive realm, but instead of truth, we're preserving probability. Got it. Now, as philosophers, we got to ask, what about probability itself? Is it something real in the world, or is it just a way we describe our beliefs?
Oh, that's a big one, isn't it? The whole objective versus subjective probability debate.
Huge debate. Some say probability reflects actual frequencies in the world. Others say it's all about our degrees of belief.
And to be honest, that debate rages on.
It does. But here's the cool thing. The formal systems we're talking about, they don't really pick sides.
Right. The mathematical structure, it's kind of neutral on that front.
So the logic works whether I think probability is like a fundamental feature of reality or just a measure of my confidence in a statement.
Pretty much. If we're modeling, say, a quantum system, then yeah, an objective view might make more sense. But if we're looking at how people make decisions with beliefs about each other, then a subjective interpretation might be better.
Different situations, different interpretations, but the logic underneath, it can stay the same. I like that flexibility.
It allows for a lot of applications. And the entry does point to some great work on the philosophy of probability itself, if listeners want to go deeper. Gillies and Eagle are good places to start.
Okay, so we can set aside that philosophical debate for now and focus on the logical mechanics. Now, the entry mentions a more recent shift in the field. It's moving away from trying to fully merge logic and probability and toward building bridges between them. What do you think that means for us as philosophers of logic?
I think it points to a more nuanced understanding of their relationship. It's less about creating some grand unified theory and more about figuring out how these qualitative and quantitative aspects, how they talk to each other, how they constrain each other.
So instead of forcing a merger, we're finding ways to translate between them.
Exactly. It's like developing a shared language so that we can move smoothly between the world of certainty and the world of likelihood. And there's some really exciting work being done on this right now. Lightgeb, Lennon Kelly, Duvin and Rott, Harrison Trainer, so many others.
Wow, yeah, the entry mentions a lot of names, so it's definitely an active area of research. Okay, let's get into the details of these probability logics. The entry talks about starting with, say, classical logic and then probabilifying it. How does that work?
Well, imagine you have your familiar logical system, propositional logic, for example, and then you introduce these probabilistic elements. There are a couple of main ways to do this.
Okay, tell me more. What are those ways?
One way is to create what's called probabilistic semantics. The actual symbols and formulas, they stay the same, but how we understand logical consequence, that's what changes. Instead of asking if truth is preserved, we ask if probability is preserved.
So the argument might look the same on paper, but we're asking a different kind of question about it. Instead of, does the conclusion have to be true? It's how certain can we be about the conclusion?
Exactly. The other way is to actually add new symbols and rules to the logic itself. This lets you write out probabilistic statements directly in the formulas. Like you could have a formula that says the probability of P is at least 0.8.
So one way changes how we think about consequence. The other changes the language itself.
That's a good way to put it.
Okay, let's start with that first one, the probabilistic semantics approach. I'm curious, how does that actually work?
All right, so in these systems, the idea of logical consequence, it becomes probabilistic. It's no longer all or nothing. And to make sense of that, we need to think about how probability functions work in propositional logic.
So we're assigning numbers to propositions.
Yes. Each proposition gets a probability between 0 and 1. And these probability functions, they have to follow the basic rules of probability. Like, probabilities can't be negative. Statements that are always true, tautologies, have a probability of 1. And if you have two mutually exclusive statements, the probability of either one being true is just the sum of their individual probabilities.
Those are the standard axioms of probability, right? But the entry makes an interesting point. It says that even these basic axioms, they depend on classical logic.
They do. Because you need classical logic to tell you what a tautology is, or what it means for two statements to be logically incompatible.
Right. So probability theory, in a way, it's built on top of logic.
It is. It's like logic provides the foundation, and probability adds another layer on top.
Okay, so we have these probability functions, but how do we use them to define validity?
Well, in this probabilistic setting, an argument is valid if, whenever all the premises have a probability of 1, meaning we're absolutely certain about them, the conclusion also has a probability of 1.
So if all our starting points are definitely true and the argument is valid, then the conclusion has to be definitely true as well.
Exactly. And here's a cool result. Classical propositional logic. It's both sound and complete with respect to this probabilistic semantics.
Whoa, what does that mean?
It means that an argument is valid in the traditional truth-preserving sense, if and only if it's also valid in this probabilistic sense, where we're preserving probability 1.
So classical logic, it's like a special case within this broader framework of probability logic. It's the case where we're only dealing with absolute certainty.
That's one way to look at it. And you could even say that the classical truth values, true and false, they're just the endpoints of this probability scale from 0 to 1.
Like, true is just probability 1 and false is probability 0. That's an interesting way to connect them.
It is. Now, there has been some debate among philosophers about whether probabilities can really be thought of as generalized truth values. Some, like Reichenbach, they thought so. But others, like Tarski and Adams, they weren't so sure. They argued that probabilities don't combine in the same way that truth values do.
That makes sense. I mean, knowing the probability of it raining and the probability of me having an umbrella, that doesn't tell me the probability of both things happening. It depends if those events are related or not.
Exactly. They're not simply additive in the same way that truth values are. Now, the entry presents a theorem, Theorem 1, which formalizes what we've been talking about. It says that if you have a deductively valid argument and all the premises have probability 1, then the conclusion will also have probability 1.
So absolute certainty, it gets carried through the argument. It makes sense. If your starting points are rock solid and your reasoning is good, your conclusion is going to be rock solid too.
Right. It's our first glimpse of how uncertainty, or rather the lack of it, can move through a logical argument.
It's a nice, clean result. But let's be real. In most philosophical arguments, we don't have absolute certainty in our premises.
That's true. And that's where the work of Ernest Adams comes in. His probability logic, it deals with those more realistic cases where our premises have some degree of uncertainty.
So instead of assuming we know everything for sure, we're acknowledging that there's a chance we could be wrong.
Exactly. And Adams wanted to figure out how that uncertainty in the premises, how it affects the uncertainty in the conclusion.
And I'm guessing it's not as simple as just adding up the uncertainties.
Well, it's actually more complicated than that. But Adams did come up with some key results. His first big result, Theorem 2, it says that for a valid argument, the uncertainty in the conclusion can't be greater than the sum of the uncertainties in the premises.
Okay, let me see if I got that. So if I have an argument with a bunch of premises and each premise has a little bit of uncertainty, then the total uncertainty in the conclusion, it's limited by adding up all those little bits of uncertainty.
Exactly. And you know what? That theorem actually includes our earlier result about probability 1 as a special case.
Really? How so?
Well, if all the premises have probability 1, then their uncertainty is 0, right?
Yeah, because uncertainty is just 1 minus the probability.
Right. So if all the uncertainties are 0, then the sum of the uncertainties is also 0. And that means the uncertainty in the conclusion has to be 0 as well.
Which means the conclusion has probability 1.
Exactly. So Theorem 2, it's like a more general version of Theorem 1. It covers cases where we have some uncertainty in our premises.
That's pretty neat. But the entry also mentions that this upper bound on uncertainty, it depends on how many premises you have. And that sounds like it could lead to some weird results. Like, what if you have a ton of premises, each with just a tiny bit of uncertainty?
That's a great point. And it actually connects to something called the lottery paradox. Imagine a huge lottery where it's extremely likely that any single ticket will lose.
Okay, I'm imagining it.
Now, if you have a premise for each ticket saying that it will lose, then according to Theorem 2, you might end up with a very high uncertainty in the conclusion that all the tickets will lose.
But we know that can't be true. One ticket has to win.
Exactly. So Theorem 2, it can give us an upper bound that's way too high, especially if we have lots of premises, some of which might not even be relevant to the conclusion.
Like if I throw in a premise about the weather, that shouldn't affect the lottery.
Right. And Adams realized this limitation. So he introduced the idea of essential premise sets and the degree of essentialness of a premise.
Okay, I'm intrigued. What are those?
So a premise is essential if the argument would fall apart without it. It's like a key building block. And the degree of essentialness, it tries to measure how important that premise is. If a premise is part of every minimal set of premises needed for the argument to work, it has a high degree of essentialness. But if it's not really needed, it has a degree of 0.
So it's like some premises are load-bearing and others are just decoration.
I like that analogy. And this leads to Theorem 4, which is an improved version of Theorem 2. It says that the uncertainty in the conclusion is bounded by a weighted sum of the uncertainties in the premises. And the weights are the degrees of essentialness.
So the more essential a premise is, the more its uncertainty contributes to the overall uncertainty in the conclusion.
Exactly. And the irrelevant premises, the ones with a degree of essentialness of 0, they don't contribute at all.
That seems much more reasonable.
It is. It gives us a more accurate picture of how uncertainty flows through the argument, focusing on the premises that really matter.
I'm following, But correct me if I'm wrong, all this talk about upper bounds, it's still about figuring out the maximum uncertainty in the conclusion.
That's right. But in many situations, we also want to know the minimum uncertainty, or in other words, the maximum probability the conclusion could have.
Right, because knowing the best case scenario can be just as important as knowing the worst case scenario.
Absolutely. And another limitation of Adams' work is that it assumes we have exact probabilities for our premises. But in reality, we often only have a range of probabilities. Like, we might say the probability of rain is between 60 and 80%.
Okay, yeah, that's much more common.
And this is where the work of Halpern and Nilsson comes in. They used a method called linear programming to figure out the optimal lower and upper bounds for the probability of the conclusion, given that the premises have probabilities within certain ranges.
So if I know the probability of premise A is somewhere between 0.6 and 0.8, and the probability of premise B is somewhere between 0.7 and 0.9, then I can use their methods to calculate the range within which the probability of the conclusion must fall.
Exactly. And they show that you can figure out these bounds just by looking at the logical structure of the argument. They also came up with the idea of Halpern probabilistic validity, which is all about whether the probability of the conclusion falls within a certain range, given the probability ranges of the premises.
Fascinating. So we can have a whole logic of probabilities even when we don't have exact numbers.
It's pretty remarkable. And the entry points out that Nilsson's work, it's actually had a big impact on AI, especially in the area of probabilistic reasoning.
Oh, interesting.
Yeah, it's led to the development of things like probabilistic argumentation systems and networks. But there's a catch. These methods, they can be computationally expensive.
Meaning they take a lot of processing power to actually run.
Exactly. So a lot of current research is focused on finding more efficient ways to do probabilistic reasoning.
Makes sense. We want our AI to be smart and fast. Okay, so we've seen how we can give classical logic a probabilistic makeover. But there's another approach, right? Where we actually add probabilistic operators to the language itself.
That's right. And these operators, they can be either qualitative or quantitative.
Qualitative versus quantitative, what's the difference?
Well, qualitative operators, they're all about comparing probabilities, like saying that something is more probable than something else, or that something is probably true, but you don't actually assign any specific numbers.
Okay, so it's more about the relative likelihoods.
Exactly. Quantitative operators, on the other hand, they let you talk about probabilities using numbers. So you can say things like, the probability of this is at least 0.7.
Makes sense. So let's start with the qualitative ones. The entry talks about Hamblin's operator, which is often written as a little box symbol.
Yes. So if you write box P, it means probably P.
Probably P. Okay, seems straightforward. But how do you interpret that probably? I mean, how probable is probably?
Well, that's where things get a little tricky. Hamblin, he thought of probably as meaning that the probability is above some threshold, usually more than 50%. But it turns out this operator, it doesn't behave like the modal operators we know from, say, epistemic logic.
It doesn't. In what way?
Well, if you know probably P and probably Q, that doesn't mean you can conclude probably P and Q.
Oh, interesting. So it doesn't follow the same rules as those standard modal logics.
It doesn't. And that means we can't use the usual Kripke semantics to interpret it. But researchers have come up with alternative semantics that can handle these non-standard operators. Like neighborhood semantics, that's one approach.
Sounds complicated.
It is. But it's necessary if we want to capture the nuances of how we use probably in everyday language.
Makes sense. Then there's that other operator, the one for at least as probable as, I think it's written as greater than or equal to.
Yes, that's the one.
Yeah.
It was introduced by Segerberg and Gardenforce. And what's really cool about it is that you can develop a whole logic for it without ever having to mention any actual numbers. It's a purely comparative logic of probability.
Wow. So we can have a logic of probabilities that's entirely about comparisons without any numerical values.
We can. It's like we're saying this is more likely than that, but we don't have to say how much more likely.
And the entry says that you can even express absolute probabilistic properties using this operator.
You can? Like if you write P is at least as probable as a tautology, that means P has probability 1. And if you write P is at least as probable as not P, that means P has probability at least 0.5.
So even without numbers, we can still talk about things being certain, or at least as likely as not.
Exactly. It's a powerful way to reason about probability without having to quantify everything precisely.
Okay, so we've seen the qualitative side. What about the quantitative operators? I'm assuming those are the ones that let us bring numbers back into the picture.
They are. The most basic kind of quantitative propositional probability logic uses formulas like this. P of phi is greater than or equal to Q, where phi is a proposition and Q is a number between 0 and 1.
So it's a very direct way of saying how probable we think something is.
It is. And the way these logics usually work is by having probability functions that assign probabilities to each possible combination of truth values for the basic propositions.
Okay, I'm following. But the entry mentions that some of these logics get even more complex. Like, they allow you to add and multiply probabilities together.
That's right. They include formulas with sums and products of probability terms. It might seem like overkill, but it allows us to express more sophisticated relationships between probabilities. Like, we can say things like, the probability of phi is equal to Q, or the probability of phi is greater than the probability of psi.
So we're not just assigning probabilities, we're comparing and manipulating them within the formulas themselves.
Exactly, and there's been some interesting research comparing the expressive power of languages with and without these extra features. Like Demi and Sack, they showed that while you can ultimately express the same things, having sums and products lets you do it in a more concise and direct way.
Makes sense. It's like having a richer set of tools to work with.
It is. And there are even more exotic operators, like the Q sub F operator.
Q sub F.
Yeah, it's a bit more technical, but basically it lets you say that the probability of something belongs to a specific set of numbers. Like you could say the probability of phi is irrational, or that it's between 0.3 and 0.4.
Wow, that's getting pretty specific.
It is. And some logics even go further, letting you express things like statistical independence using polynomial weight formulas.
Okay, now we're getting into some serious math.
We are. But the key takeaway is that these different operators and features, they allow us to capture more and more of the subtlety of probabilistic reasoning within our logical systems.
It's like we're building up a whole new language for talking about uncertainty. Now, one thing that often comes up when we talk about logical systems is their metalogical properties, like compactness and completeness. And the entry mentions that propositional probability logics, they often lack compactness. What does that mean, and why does it matter?
Compactness is this nice property where if every finite part of a set of formulas is consistent, meaning you can find a model that makes them all true, then the whole set is also consistent. But probability logics, they can sometimes violate this property. You can have an infinite set of probabilistic constraints that are all individually okay, but you can't satisfy all of them at the same time.
So it's like trying to fit an infinite number of puzzle pieces together, even though any finite number of them would fit just fine.
That's a good analogy. And this lack of compactness, it can make it harder to prove things about these logics. Like, you might be able to prove that every valid formula is provable, but not that every consequence of a set of formulas is also provable. That's the difference between weak and strong completeness.
Right, it's about how powerful your proof system is. And the entry mentions that some probability logics have strong completeness, but often you need special rules or restrictions to achieve it.
That's right. It's a reminder that dealing with probabilities within logic, it's not always a walk in the park.
Definitely not a walk in the park. Okay, let's move on to modal probability logic. As the name suggests, it's about combining modal logic with probability.
It is. So you remember how modal logic is all about possible worlds?
Of course, it's about what's necessary and what's possible.
Right. Now, in modal probability logic, we not only have possible worlds, but we also assign probabilities to those worlds, or even more generally, we associate whole probability spaces with each world.
So instead of just saying it's possible that P, we can say it's probable to a certain degree that P.
More than that, actually. You can have probabilities within probabilities. Like, you can talk about the probability of an agent believing something with a certain probability.
Whoa, that's layers of uncertainty.
It is. And this framework has been used to model all sorts of things, from systems where states change randomly to scenarios where agents have beliefs about each other. And the same logical structure can often be interpreted in both ways.
It sounds like a very versatile framework. Now, how do we actually define these modal probability models?
Well, a basic finite model, it starts with a set of possible worlds, just like in regular modal logic. But for each world, we have a function that assigns a probability distribution over those worlds.
So it's like saying, from this world, there's a certain chance of ending up in that world, and another chance of ending up in that other world, and so on.
Exactly. And then we also have a valuation function that tells us which atomic propositions are true in each world.
So we know which basic facts hold in each possible world.
Right. And then a probabilistic formula like P of E is greater than or equal to Q. It's true in a world if the sum of the probabilities of all the worlds where phi is true, according to the probability distribution for that world, is greater than or equal to Q.
Okay, I think I'm following. But the entry also mentions a generalization where these probability distributions are indexed not just by the world, but also by, like, actions or agents.
That's right. So instead of just having P of phi, you might have P sub A of phi, where A could stand for an action or an agent.
So different actions or agents might have different probabilities for the same event.
Exactly. Like the probability of the light turning on might depend on which switch you flip. Or the probability of someone taking a certain action might depend on their beliefs and goals.
Right, it makes sense. And the entry gives a really detailed example with actions and propositions, showing how you can model probabilistic transitions between states, and even how agents reason about each other's beliefs and choices.
It's a great example, and it really highlights how powerful this framework is, especially for analyzing strategic interactions where agents have incomplete information. It even touches on some classic philosophical puzzles, like Miller's principle and the Judy Benjamin problem.
Okay, I'll have to look those up. Now, the entry gets even more technical when it talks about using full-blown probability spaces in modal probability logic.
Ah, yes, those sigma algebras and measures, they might seem intimidating, but they're really just there to make sure everything stays mathematically rigorous.
So it's like the foundation that ensures the probability calculations make sense.
Exactly. It's especially important when we're dealing with infinite sets of possible worlds, where things can get a bit tricky. And in these more general models, each world can actually have its own probability space, reflecting uncertainty about both which world is the actual one and what the probability structure of that world is.
It's like saying, not only are we uncertain about what's true, but we're also uncertain about how uncertainty itself works in different possible worlds.
That's a great way to put it. It's uncertainty all the way down.
Mind-blowing. Now, the entry also talks about combining quantitative probability with qualitative uncertainty, like belief.
Right. That's a key area where researchers are trying to build those bridges between logic and probability that we talked about earlier.
So how do we do that? How do we mix numbers and beliefs?
One way is to simply add a modal operator for knowledge or belief, like the box operator, to our probability models. So we can have formulas that combine probabilistic statements with statements about what agents know or believe.
So you could have a formula that says something like, the agent knows that the probability of 5 is 0.5.
Exactly. And the entry gives a nice example with a coin flip, where we're uncertain about both the outcome of the flip and whether the coin is fair or biased.
It's a great illustration of how those two kinds of uncertainty can interact. But the entry also mentions that we need to be careful when we combine these quantitative and qualitative elements. There might be constraints on how they relate to each other.
That's right. We want to make sure our beliefs and our probability assignments are consistent with each other. Like, if I believe something with absolute certainty, then I should also assign it a probability of 1.
That seems reasonable. And the entry discusses some approaches to defining belief in terms of probability, using thresholds, or the idea that belief is just probability 1.
It's a fascinating area where we're trying to figure out the precise relationship between our qualitative judgments and our quantitative assessments of uncertainty.
It's like we're mapping out the terrain between those two ways of thinking about uncertainty. Finally, the entry mentions dynamics in the context of modal probability logic. What kind of dynamics are we talking about?
It's all about how the probabilities associated with possible worlds change over time. And this is especially relevant when we're thinking about agents updating their beliefs based on new information.
So as we learn new things, our beliefs become more or less certain, and we can model that using probabilities.
Exactly. Conditional probability plays a big role here. Like, if I learn that event A has happened, that might change my belief about the probability of event B.
Right, because A and B might be related somehow.
They might. And the entry introduces an operator for updating beliefs based on new information. It distinguishes between updating the whole probability model versus just calculating a conditional probability within the existing model.
Okay, so there are subtle but important differences in how we think about updating our beliefs. It seems like a very rich area for exploring the logic of belief change. Now, the last section of the entry, it deals with first-order probability logic.
Ah, yes.
Yeah.
This is where we bring in the full power of first-order logic with quantifiers and predicates and combine it with probability.
So now we can talk about probabilistic properties of individuals, not just events.
Exactly. And a classic example is the statement, more than 75% of all birds fly.
Okay, yeah, that's a statement about a whole population, not just a single bird.
Right. And to express that, we need probabilistic quantifiers that can range over individuals in a domain.
And that's different from saying the probability that Tweety flies is 0.9, which is about a specific individual.
Precisely. One is about statistical properties of a group. The other is about the uncertain attribution of a property to a specific individual.
Okay, I'm with you. So how does first-order probability logic actually work?
Well, the entry gives a nice example of a simple system that includes a probabilistic quantifier. It's written as Px of phi is greater than or equal to q, and it means the probability of randomly picking an individual x that satisfies phi is at least q.
So phi could be something like is a bird, and q would be the probability.
Exactly. And the models for this logic, they have a domain of individuals, an interpretation function that tells us what the predicates and functions mean, and a probability function that assigns probabilities to each individual in the domain.
And the entry uses the example of a vase with black and white marbles, where the probability of picking a black marble depends on how many black marbles there are and how they're distributed.
It's a very clear illustration. And then the entry goes on to describe some natural extensions of this basic logic.